So the next topic is Nilpotent Transformations, the next canonical form. Before we start the section though, let us quickly see what the main thing in the previous section was. What was the main result that we established in the previous section? We had a finite dimensional vector space V and a linear operator T on V, an element T in the operator algebra A of V. And this T had a condition on it. All the characteristic roots of T lie in F, where F is the underlying field of course. Then T can be put in triangular form. That's the vague way of stating what actually is just this. Then there exists a basis D of V such that the matrix of T with respect to B, that is this matrix, is triangular. Okay. So there may be many operators having this property, many of them won't have this property. Those that have can be triangularized. Okay, they can be put in triangular form like this. There will be at least one basis with respect to which the matrix of T will be triangular. In particular, nilpotent transformations or nilpotent operators have this property. Why? Because if your T in particular is nilpotent, then all its characteristic roots are 0. And that's why all of them belong to F in a trivial manner. So nilpotent transformations also can be triangularized. Unfortunately, this alone is not enough for many purposes. We need extra information. And that is why in this section we are going to find good canonical forms for specifically for nilpotent transformations, and then we will also find good canonical forms for other transformations, other types of transformations. Now, one may think that this is really not worth it, given that the nilpotent transformations form a very small class of all possible transformations. Still, we will see that this study will have its own advantages. Now, before we start with the first lemma of this section, there is something else that the author says. This can be done in two distinct ways. One of the approaches the author calls the ground-up approach, which is what we have been following so far. That is, we just develop everything from scratch. There is another thing that one can do, there is another approach, where we use module theory. The results from the section on modules, which was the last section in the vector space chapter, which we have already seen. So, which one of those two approaches would be taken in developing these parts? The author has decided to use the ground-up approach for this section and the next one, and the module theoretic approach for the next one, the one after that. So we do not have to worry about modules right now itself. Instead, let's just straight away start with the next lemma. Now this next lemma is not specifically about nilpotent transformations, but it's for general transformations. For some reason we are going to see it now only. It will prove helpful. So let's see the lemma. This is going to be 6, 5, 1. So we start with a vector space which is a direct sum of some other vector spaces. V is the direct sum of these Vi's, k number of V. K of course is a positive integer, where the dimension of Vi over F is the underlying field of scalars is Ni, and there is a condition on these Vi's. Each Vi is invariant under a linear operator. Under some t which is a linear operator on V. So this entire thing is the hypothesis of the statement, and then we will say then what happens. That will be the conclusion. But before we write the conclusion, let us just stop here itself and think a little bit about this statement. Each Vi is invariant under T. Does it make sense? If so, what does it mean actually? Let us go back to the definition of invariant subspace. You have a vector space V, you have a subspace W of V, and you have a linear operator T on V. What does it mean to say that W is invariant under T? It means that the image of W under T, don't forget that we are consistently writing mappings to the right, okay, that's why it looks like this, is contained in W. When this happens, we say that W is invariant under T. That is, applying T on any vector of W does not get you outside of W, it keeps you inside of W. Fine, we already know this. But the problem is Vi a subspace of V? If you simply think, it's not actually. Why? That's because for Vi to be a subspace of V, Vi first of all has to be a subset of V. But that is not strictly speaking true, because the elements of Vi are just some vectors. Say V is a vector in Vi. Whereas the elements in V are not that type of vector. They are k tuples of vectors. So what does this statement even mean? See, it means in this sense. This is the meaning of this statement. You may remember that when you form a direct product a direct sum like this, you very naturally find subspaces of V isomorphic to these Vi's. To be more specific, say we think of V1. V1 itself is not a subspace of V if we are strictly thinking of the things. However, capital V has a subspace that is isomorphic to V1, and that subspace is this. That subspace is this. This is a legitimate subspace of V, and this is isomorphic to V1. So when we say that Vi is invariant under T, really we mean that this subspace is invariant under T. But because there is no real useful distinction between isomorphic vector spaces, so we just simply say that Vi is invariant under T. Alright. So having understood this, next see the conclusion. Then what happens? Then there exists a basis of V such that the matrix of T with respect to WRT, this basis is, it will have a form, okay, that form looks like this. Where it's an ordinary matrix whose entries are coming from the underlying field capital F, but it has been written in block form. So these individual symbols that you are looking at are not necessarily scalars, but arrays of scalars. So we have grouped some parts of the original matrix into blocks, and here you are looking at those blocks. When talking about these blocks, we do not normally call them blocks or arrays, we call themselves as matrices. So the next thing is where AI is an Ni by Ni matrix, but that does not mean that these are actually matrix as entries in this matrix. No, that's not the meaning. It just means that A1, for example, is an N1 by N1 array, where AI is an Ni by Ni matrix. And is in fact the matrix of the operator that T induces on the subspace Vi. If you restrict T on, the original linear operator T is a function from V to V. If you restrict that to Vi, then it becomes the restriction with new domain Vi. But because Vi is invariant under T, you can change the other set also from V to Vi. So then it will become an operator on Vi itself. So the restriction of T on Vi itself is an operator, so it will also have its own matrix. That matrix is AI. Okay. So this is the claim. Now let's see the proof. The proof actually is very easy. It's just seeing one thing and then the entire thing follows from that almost immediately. So the proof starts by considering bases for these individual VIs. Let let me write like this, because the notation is going to be somewhat complicated. Won't say complicated, but a little messy, with subscript and superscript. N11 BA basis of V1 V1 to Vn2 to be a basis of V2. You can understand why we are using superscript. That's because we do not have one or two vector spaces but an arbitrary number of them, k of them. So we need to not only number them within a given basis for which we are using suffix subscript, we also need to identify them as belonging to the basis of some Vi. So we need to do that also, and that is why we are using the superscript. This one that you see as superscript indicates that a vector having that as superscript belongs to the basis of V1. If you see 2, then it belongs to the basis of V2, like that. B a basis of V2, like that. V1k Vnkk be a basis of Pk. Also, do not forget that these are the dimensions of the respective vector spaces. That's why we have n1 here, n2 here, and nk there. Then the ordered set will this will take some space, where what we do, we just write all the vectors that we encounter here in that order in which they are originally appearing, and we essentially take the union of these bases, but within this set we maintain the order in which we are writing the vectors there. V1 2 Vn2 to V1k Vnk k. It turns out that this is a basis of V, and I won't prove it. I am leaving this to you, but I will give some hints though how to prove it. I mean, you already know how to prove it, but still I will tell you some points about proving this. What is it that you have to do to prove that this is the basis for V? You have to prove two things. One of them is that these vectors are linearly independent, or this set is linearly independent over the underlying field F. And the second thing is that it spans the space V. Now, in doing these two things, you keep in mind one thing. Do not forget that V is the direct sum of these spaces, which means what? It also means two things. One of them is that any vector V in V is expressible as a sum of vectors coming from, this one comes from here, this one comes from here, this one comes from here. It may look a little strange, okay? you may have already got really confused, because as I said, this is a Cartesian product. But all these things that I am talking about now, that V1 belongs to this, V2 belongs to this, keeping that isomorphism in mind, when we say V1, actually we are thinking of that subspace in capital V which is isomorphic to V1. Right. So V is, in fact, V can also be thought of as a direct sum of those subspaces. In that sense, if you think, then things will become easy. So keeping that in mind, you have two things that this entire thing is telling you. One of them is that V is a sum of some vectors coming from those spaces. That is the first thing. And the second thing is that such an expression, expressing V as a sum of vectors coming from these spaces, is unique. The first fact that V can be written like this will be used in proving that this spans V. Why? Because V1 belongs to V, so V1 itself will be a linear combination of these vectors. V2 itself will be a linear combination of these vectors, and Vk will be a linear combination of these vectors. So I have essentially told you the proof itself. You combine those linear combinations, you get a linear combination of these vectors, and that's how you obtain any vector in V as a linear combination of these vectors. So they span V. And in showing that they are linearly independent, what will you do? You will take a linear combination of these vectors and set that to 0. Then you club the vectors from the entire linear combination into chunks. You imagine this part of the linear combination as one vector V1, this part of the linear combination as another vector V2. Okay, so that way you see that your linear combination is, after all, a sum like this. You have set that equal to 0. 0 can also be expressed as 0 plus 0 plus 0. So the uniqueness of these sums would tell you that each such vector individually has to be equal to 0. And then each vector means what? Each vector means a linear combination of these vectors, that is 0. A linear combination of these vectors, that is 0. A linear combination of these vectors, that is also 0. Then you just use the fact that these sets are linearly independent. That will give you all scalars equal to 0. That's it. So we can just simply say that this is a basis for V. Or I can write like this. One can prove that, and it's better I give it a name. B is a basis for V over F. And now comes the matrix. If the matrix of the induced operator should I give it some name? No, the author hasn't given it any name and we won't need it. So let me write like this. if the matrix of the induced operator on Vi by T is Ai, then this is not enough. No, if matrix with respect to what? With respect to which basis? With respect to the ith basis. Nii is Ai. Then Ai is obviously an Ni by Ni matrix. That's the first thing. And the second thing, which is extremely easy to verify, is that the matrix of T with respect to B will have that desired form. Is an Ni by Ni matrix, and the matrix of T with respect to B is this. Now you may have some doubt about this part, this last part. So to clear this up, let me take a small example. Not an actual example, but an example that shows the pattern in which you will have this matrix. Just to show that yes, this is how the matrix is going to look. According to how the proof went, let me take this small example. Say V is equal to V1 plus V2 plus V3, where dimension of V1 is 1, dimension of V2 is 3, and dimension of V3 is 2, say. And suppose there is a linear operator T on V such that these are all invariant under T. Okay, now you choose bases for these vector spaces. To keep the notation simple, we are not going to take V1, 1, not those things. Just simple, straightforward V1, V2, V3. Okay, so this is a basis for V1. This is, we have 3 here, no? V4, and say V5, V6. This is a basis for V3. All right. Now you know that in order to calculate the basis of, the matrix of T with respect to this basis, V1, V2, V3, what do we have to do? You have to apply T on each basis vector and see what happens. Say I do that actually. V1t. Because capital V1 is invariant under T, so that is again going to land in V1 itself. Since this is a basis of V1, I will have something here, say alpha V1. That's it. That means the other vectors are going to come with 0 coefficients in that linear combination. What about V2t? V2t is going to have, and in fact there is no need to write anything here, just give star. We just need to see the pattern, right? In V2, in capital V2, this is the basis, and T, V2 is invariant under T. So when you apply T on any vector from V2, that is going to again land in V2. So that will be a linear combination of V2, V3 and V4. So V2t is going to look like this, something times V2 plus something times V3 plus something times V4. The coefficients of V1, V5, V6 are going to be 0 there. Okay, so let me just simply write 0 V1 plus this plus 0 V5 plus 0 V6. And the same is going to be the case with V3t and V4t also. V3t and V4t are also going to look like this with possibly different star coefficients. Similarly, what will happen to V5t, since V3 is invariant under T, so V5t is going to again land in V3. So it will be a linear combination of V5 and V6. So all the other vectors are going to come with 0 coefficients. Star V5 plus star V6. And the same thing is going to happen to V6t also. It also is going to look like that. Now if you write the matrices, in fact now if you write the matrix of T itself as a whole, what do you have to do? Because we are writing functions to the right, this is one advantage while writing matrices. You just take the coefficients and write them in the manner they appear in these equations. You do not have to make rows, columns, you don't have to do those things. So you just straight away start writing the coefficients. The first row is going to look like this. And this time I am going to write everything, okay. So 1, 2, 3, 4, 5, 6. For V2, we start with 0, then star, 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 and then 0, 0. For V3 also, the pattern is like that. For V4 also, the pattern is like that. For V5t, those are the coefficients. All these first coefficients are 0 except the last two, which they may also be 0, but in general they may be something else also. For V6t also, that's the thing. This is the so-called 0 pattern of the matrix of T. Now if you look carefully, this matrix can be divided into blocks like this. This block is your A1. And in fact, if one is thinking about the matrix of the operator that T induces on V1 with respect to the basis that's singular V1, this is the matrix. This is the matrix of the operator T induces on V1. This one is the matrix of the operator T induces on V2. It's a 1 by 1 matrix. This is a 3 by 3 matrix. This is A2. This is a 2 by 2 matrix A3. And those zeros that you saw now, these are the zero blocks. This is 1 0, this is another 0, this is another 0, this is another 0, this is another 0. And instead of writing like this, we normally write like this. It's just that. So the individual entries themselves don't matter, but the pattern matters. And all of these things are happening because we have considered a direct sum. That is why directly just concatenating the bases one after another of the individual spaces has given us a basis for the entire space. And everything is happening so nicely that they don't interfere in each other's matter. The matrices neatly get their own place in this larger matrix, which is the matrix of T. You can now see why the general case is like that. All right. Now that this elementary lemma is out of our way, we can see another lemma which is more important. We are going to need these things when we do our main thing. And this one is about a linear operator, that is nilpotent. If T belonging to A of V is nilpotent, all right, then for any scalars alpha naught, alpha 1, etc. up to alpha m in F with alpha naught non-zero, the operator alpha naught plus alpha 1 t plus alpha 2 t square, etc. plus alpha m t to the power m is invertible or regular. It's not singular. That means it has an inverse. There is a result which is more general than this, which also is essentially the same in ring theory. We will, however, do it separately. We will prove it. But essentially the proof that we see here of this fact, there is a general proof in ring theory also. The proof starts by noting this. Let S be an operator on V, be nilpotent, and because S is nilpotent, some power of S is going to be 0. That's the definition of nilpotence. Say S to the power R is equal to 0, where R is a positive integer, a natural number. Okay. Then one can verify the following. This product alpha naught plus S times won't have that much space, right? So let me write here 1 over alpha naught minus s over alpha naught square plus s square over alpha naught cube minus and so on plus minus 1 to the power r minus 1 s to the power r minus 1 divided by alpha naught to the power r is equal to 1. 1 is of course the identity operator. You see that this makes sense because alpha naught is non-zero, and that is why its inverse in the field, multiplicative inverse in the field exists. So 1 over alpha naught means just that. So you can interpret this, for example, this term as the inverse of the square of alpha naught. Since alpha naught is non-zero and we are in a field, so its square is also non-zero because fields are integral domains. So these higher powers of alpha naught, all of them are going to be having inverses in the field. So we are multiplying the powers of S by these inverses with appropriate signs. It turns out that when you multiply these two operators, this is one operator, this is another operator, in the operator algebra, you get the identity operator. Now, you have to actually carry out the multiplication. You can do it like how you usually do algebraic calculations, because this calculation, this product will happen where? In this algebra. So you have all the rules that are there in the algebra, distributive law, everything. Okay. So you use those things. One more thing, because only powers of S are involved, so that terms also commute with one another. That thing is also there. So you just carry out the multiplication, you will see that there will be many cancellations. And after all cancellations, you will be left with 1. In fact, you can see where this 1 is coming from multiplying alpha naught and this. Oh, and one more thing. Do not forget that when we write alpha naught plus s, it has its own meaning. Can you add a scalar and an operator? No. You can only add two operators. Alpha naught is the short way of writing alpha naught 1. Okay, for that matter, this is also 1 over alpha naught 1. So with that understanding, what we see here is that if you add a non-zero scalar to a nilpotent operator, then that the resulting operator is invertible, because this is the inverse of alpha naught plus s. So is invertible. We are now going to use this fact to prove that our operator is invertible. Now, consider the operator S equal to alpha 1 t plus alpha 2 t square and so on plus alpha m t to the power m. Okay, so whatever we did here in the first half of the proof was about a general nilpotent operator capital S. Now we are considering this particular operator as S, where we have all these, we already had those scalars in the statement itself. But is it nilpotent? Let's see. What we are given though is that T is nilpotent, since T is nilpotent, so some power of T is going to be 0 for some r belonging to n, then the rth power of s is also equal to 0. The author asks how or why is it true. I am also asking this to you. Why is it true? Why should the rth power of s also have to be 0? And I leave this to you with one hint though. And the hint is this. Two hints actually. So once you know that this is true, then now you understand that yes, our S is also nilpotent. But why is that true? You look at S, what S is carefully. You can see that each term has T, right? So you can take one T common out. Now if you raise S to the rth power, the exponent gets distributed over both the factors. I mean, the rth power of this product is t to the power r times this other thing to the power r. Why? That happens only when the operators commute with each other. Do these operators commute? One of them is t and the other one is this. Yes, they commute, because this other one involves again only powers of t. So whether you take out t on this side or on that side, it does not really matter. Both of them are equal to s. And that is why you have this. And I won't say anything else, okay? Actually, this is in fact everything that you need to say that s to the power r is 0. And that's why I'm just simply going to continue from here. So now we know that this s is nilpotent. So s is nilpotent. And that is why, by what we did in the first half of the proof, alpha naught plus s, which is this, is invertible. Okay, so that completes the proof. Now let us next see one notation, and then we will then after that there is one small definition, and then we will state the main theorem, the key theorem of this section, but we won't prove it in this video. We will prove it in the next video. We are going to use a notation for a special type of matrices, and those matrices are going to appear as blocks in some canonical forms. So we are going to need this type of matrices in whatever we are going to see next. So that is why we have this notation. The notation is going to save us from writing these matrices again and again fully by MT we mean the following T by T matrix all of whose entries are 0 except the entries in the super diagonal. Except the ones on the super diagonal, all of which are 1. Let me give you one specific example, then you will understand. Say M3. M3 will be a 3 by 3 matrix. What do we mean by super diagonal? Let me just write these extreme corner elements. In the middle you have one more element which is also 0. The super diagonal of a square matrix is the diagonal above the diagonal. This is the leading diagonal, this is the super diagonal. This is M3. Okay. And like that we have other M's also. Now after this notation, you have one definition, small definition, it's called degree of nilpotence of a nilpotent matrix. This is available in general in ring theory also, because if you are familiar with that part of ring theory, that part means it's just an elementary thing. In a ring also you have nilpotent elements, right? And it makes sense also. That is because our algebra is also, besides being vector space, it's also a ring. So the nilpotent linear operators are just the nilpotent elements of this ring. Let T belonging to A of V be a nilpotent operator. We call a positive integer k. The degree of nilpotence in this text, it's called index of nilpotence, same thing. The index of nilpotence of T if the kth power of T is 0, but no smaller power is 0. But this is non-zero. So the degree of nilpotence is the smallest positive index for which the corresponding power of T is the 0 operator. And now let me finally state the key theorem of this section and then we will stop. this is about a nilpotent operator. So this is theorem 651. Let T belonging to A of V be nilpotent with it's not degree, it's index of nilpotence have to stick to the exact term n1. Then V has a basis. V has a basis with respect to which the matrix of T is of the following form. Again, we are going to see a block diagonal matrix. I mean a block matrix in which the diagonal blocks are where we may have non-zero elements, elsewhere we have zero elements. M, N, R. So these M's are those empties where the N's are appearing in decreasing order and the sum of these N's is equal to the dimension of the underlying vector space. Okay, so this is the result, and you can see that here, unlike in other matrices, I mean for example the previous result, I mean the one before that, we do know what the entries in these blocks are, because these empties are those matrices. The only thing that can change in the present situation depending on what T actually is are these N1, N2, these things, and they are numbered in fact in R. However, whatever these numbers are, their sum should be the dimension of the original vector space. Okay, so we will see the proof in the next linear algebra video. So that's just it for tonight. Tomorrow also we have, do we have video or community post? I'm not sure, I forgot actually. So we will see what we have tomorrow. So see you tomorrow either in a video or in a community post. Until then, this is me, Lucifer from A Mathematical Room. Have a nice day.